Uh, Hello everyone, Georg from JLPTDOU here, and today I'll be showing you an overview of the technology behind JLPTDOU, and then at the end I'll show you how I'm using vector embeddings in JLPTDOU. Alright, so let's just get right into it and I'll show you the broad architecture behind the website. So here you see a sketch of the architecture. You see the user on the left side, so the user uses a browser to access the website, and then you see all these things here. They are the components of my website, all the infrastructure that is required to run it, and all these things that are inside of this blue border, all these things are self-hosted. And everything outside of the blue border is accessed using the internet. So we see here that the user communicates via the internet with Nginx server. That's a web server that hosts the front end and forwards the requests to the Python backend. So it serves the front end and forwards the requests to the backend. There's a Python backend server. That's a simple web server that processes the requests that are sent by the user. This backend server saves data to the Redis database and can also read data from the Redis database to then forward it back to the user. The other big task of the Python backend is that it puts messages via RabbitMQ on a queue, and there's other Python background servers that read those messages from RabbitMQ. These Python background servers read those messages and process the messages. They read data from the Redis database and also write to the database. And when they have a task that requires communication with OpenAI, they send requests via the internet to the OpenAI API and use the responses and save them to the database. So for example, when there's some voice file to be generated, they call the OpenAI API to generate the voice file and then save the voice file to disk. Okay, so that's what is inside the internet border, so everything that I'm hosting myself using Docker. Another thing that is outside and is not hosted by myself is the Google authentication. So if the user wants to log in using the Google authentication, then the user communicates a bit with the Google server, and my backend also communicates with the Google authentication server. But if the user doesn't use Google login, then that's not required. So those are all the different parts that I'm hosting myself, everything inside of the blue border. And let's look at a table of, again, just which components I'm hosting. So here on the left you see different kinds of Docker containers that I'm hosting. There's an Nginx container, a Redis container, there is Python backend, there's a RabbitMQ container, and there's multiple background servers. And on the right side you can see again the responsibilities of those different servers. So the Nginx hosts the front end and redirects requests to the back end. The Redis database is my primary database. It stores a lot of different things. It stores different the chat histories. It stores the vocabulary. It stores vector embeddings of vocabulary and much more. Then we have the Python backend that hosts the web server, so all the requests that the user sends, they are all hosted and replied to by the Python backend. and this Python backend puts a lot of background tasks on the queue. The RabbitMQ is a simple FIFO queue, and the background servers, they read from the queue and process these messages and save the results to the Redis database. The reason why there's a queue server is that the front end should not, or the web server rather, should not be blocked when there are long tasks that take a long time. So instead of blocking and instead of waiting for the results, instead these tasks that take longer are put on a queue, and then the queue is the tasks are processed from the queue, and that way there's no blocking, and the web server can reply to all those requests that the front end sends. Since that was a bit complicated, and I'm sure it's not really clear, let's just look at a simple example. What happens when there is a request by the user. So the example here is that the user sends a simple message in a conversation. So here on the screen you see simply that the user has opened a conversation with the Hayato agent over here. The agent has sent a message and the user is ready to start the conversation. So let's look at the next step. Here we see that the user has sent a message, Genki desu, kyou wa nani o shitemasu ka? So that's the message that the user sent. We see over here that there are 3 dots, so that indicates that the agent is replying. And here simply the user has sent a message, and we see that the message is not yet translated, so it's only the Japanese message. So next, let's look how this message travels through our system, let's say. So here the user sends the message. We see this big arrow, it reaches the Python backend. This backend then creates a lot of different tasks and puts those tasks on the queue. They are respond to message, translate message, and create audio file. There's lots of other tasks. There's a few more put on the queue, but I didn't list them up here. So those tasks are put on the background queue, and the message that the user has sent is saved to the database. Next, the background servers read those queues and process these messages that were put on the queue. So now the background servers respond to the message, translate the message, and create audio files. And to do so, they communicate with the Redis database, so they read all the different context and read the conversation from the database. Then they call the OpenAI API for responses by the AI agents and for the audio files. So there's lots of calls going on to the OpenAI API. And the results are saved back to the database. So here we see that a new message has been saved. That's the response by the AI agent, kyou wa shigoto shitemasu. So that's the new message that was saved. And in the next step, we see here how the user receives those new messages. So the user sends a new request to the backend, and the backend checks the database, and it sees, oh, there's a new message, and the new message is sent back to the user. And then the user gets this result. So the user has received a new message from the AI agent, and we also see that here the user message is now translated. So all these results have been generated and served back to the user. Alright, so that was the example of how the broad architecture works of JLPTDOU. That was just a simple overview, and let's look at one new feature, and let's look now at how vector embeddings are used in JLPTDOU. Alright, so first of all, I'd just like to refresh your memory of what vector embeddings are. Vector embeddings represent data as a vector in n-dimensional space. So this data that is represented as vector embeddings could be anything, most commonly text or images. And these embeddings, so those vectors, they can be used for lots of different things. For example, they can be used for clustering, for similarity analysis or compression, and many more applications of vector embeddings. On the left side here you can see an example of a vector embedding. So you see different data points, that's all these points in our graph. And you see that these points have different positions inside this n-dimensional space. In this image it's just a 3-dimensional space, since humans can't visualize more, but commonly in vector embeddings this n-dimensional space can be much larger, let's say more than 1,000 dimensions. But let's look at this example, and we see that those texts, so banana, apple, wolf, dog and cat, they are all mapped to a vector, here visualized as a point. And the interesting thing in vector embeddings is that the relationship between those between the encoded data is then also present in those in this geographic n-dimensional space. So simply as an example, here we see that the distance between the point for dog and the point for cat is much smaller than the distance between the point for cat and the point for apple. And that simply means that the word wolf and the word dog and the word cat are more closely related than the word cat and apple, simply due to this increased distance between apple and cat. And we can also see that apple and banana are quite close to each other, so they are closely related, and these three words, wolf, dog and cat, are close to each other, so they are related. There's other properties to explore in vector embeddings, but that's just our example here. Vectors that are close to each other, they tend to mean something similar. So let's look at how we can use this property in JLPTDOU. Okay, I'm sorry, first of all, I'd just like to show you how we are obtaining vector embeddings. So we have the Python backend. Then this Python backend builds a string representation of a vocabulary. So Natsu, the word for summer, is then represented as using the kanji Natsu / Natsu and summer. This string representation is sent to the OpenAI embedding API, which we see over here. The embedding API returns a vector representation. This vector representation is also saved to the Redis database, so it can be accessed later on without having to call the OpenAI embedding API. So that's how the JLPTDOU builds vector representations, vector embeddings of vocabulary. And now let's look at how these vector embeddings are used. Okay, on this screen you see the vocabulary explanation for the vocabulary summer. So here we see the name again, Natsu, summer. we see an explanation, example sentences, and here at the bottom we see related words. And these related words, they are obtained using vector embeddings. So to do so, the vector embedding for summer is taken, and then the backend looks up which other vector embeddings are the closest to that vector embedding, and the vocabulary associated with those embeddings are then returned and shown to the user as being related words. So we see that here the word Natsuyasumi, Aki, Atsui and Shiki are closely related to the summer vocabulary, and those are the words obtained using vector embeddings. They have the closest vector embedding to the vector embedding of the word summer, so they are most related, and they are shown to the user on the vocabulary explanation page. That's how I'm using vector embeddings for JLPTDOU. That's it. Thanks for watching. I know that was just a broad overview of my architecture and of vector embeddings. If there are any questions, please don't hesitate to ask. I'm happy to help you and reply to you and tell you more about some detail you want to know. So thanks for watching. Goran itadaki arigatou gozaimasu.